$2 million. Gone. Not because of bad code, not because of the wrong tech stack, because of a law that existed since 1967, and not a single person on that team had ever heard of it. I was the external architect brought in for the postmortem. A major Korean financial institution had spent 18 months migrating their monolith to microservices. The result? A distributed monolith, every service tightly coupled, latency through the roof, deployments cascading into failure. When I mapped their service boundaries against their org chart, the match was exact. Payments team owned the payment service, risk team owned risk, compliance owned compliance. Every cross-boundary transaction required a meeting between departments just to change a field name. This is Conway's law, articulated by in 1967. Any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. They didn't build microservices. They built a software replica of their dysfunctional org silos. The tragedy? This law is in every software architecture textbook, but nobody made them read it before the project kicked off. By the end of this lecture, you will know all 56 laws, and more importantly, you will know exactly which one is about to kill your current project. Now, here is where most project managers make the exact same mistake, and I have watched it happen at least a dozen times across 25 years. The same financial institution, 6 months into the crisis, had a new deadline imposed by the board. The project was already 4 months late. The PM's instinct? Add more people. 8 senior developers were brought in from 3 different outsourcing firms. I was still on site. With 3 weeks, the original team was spending more time in onboarding sessions and Slack threads explaining architecture than actually writing code. The new developers introduced integration bugs that the original team then had to fix. The project shipped not 1 month late, not 2, but 4 additional months after the reinforcements arrived. This is Brooks's Law, coined by Fred Brooks in his 1975 masterpiece, The Mythical Man Month. Adding manpower to a late software project makes it later. The mechanism is not mysterious. Every new developer added to a team creates n new communication channels, and each channel consumes existing developer bandwidth. 8 new people meant 36 new pairwise communication links that did not exist the day before. But here is what makes this dangerous for your career. Brooks's Law has a nuance that most people miss entirely. And that nuance is exactly what separates a junior reaction from a senior decision. We will get to that in Cluster 2. Let me be very direct about what this lecture is and what it is not. This is not a glossary. I am not here to read you 56 definitions so you can close the tab, having learned nothing actionable. Every single one of these 56 laws maps to a decision point you will face, or are facing right now, in your career as a senior developer, a tech lead, or an architect. Here is the concrete promise. After this lecture, you will be able to do 3 things. First, you will be able to run a premortem. Before a project launches, you will walk into an architecture review and identify which of these laws are at risk of being violated, and raise that flag with evidence, not instinct. Second, you will be able to do a postmortem with precision. When a project fails, you will map the failure to a specific law, explain the mechanism, and propose a structural fix, not a blame assignment. Third, you will be able to speak the language of engineering laws in design discussions, which is the single biggest credibility signal that separates a senior developer from a staff engineer. And for those of you preparing for the Information Management Professional Engineer certification, I have marked the laws that appear most frequently in exam questions. You will not need a separate study guide. Now, do you know what the single most dangerous gap is between a 5-year developer and a 10-year developer? It is not technical skill. The answer is coming in the next scene. The single most dangerous gap between a 5-year developer and a 10-year developer is not knowledge of algorithms or cloud architecture. It is the absence of a mental model, a structured map of how software systems actually behave over time, under organizational pressure, and at scale. These 56 laws are that mental model, and I have organized them into 7 clusters so you can navigate them like a senior engineer, not memorize them like a student. Cluster 1 covers complexity laws, why systems always grow harder to change, no matter how clean your initial design was. Cluster 2 is organization laws, Conway, Brooks, and the laws that govern how human structure shapes software structure. Cluster 3 is quality laws, the economics of defects, technical debt, and why shortcuts always compound. Cluster 4 is performance laws, Amdahl, Little, and the laws that explain why your optimization did not work. Cluster 5 is communication laws, how information degrades across teams and interfaces. Cluster 6 is estimation laws, Hofstadter, Parkinson, and why every project estimate is wrong by default. And Cluster 7 is change laws, Lehman's laws of software evolution, and why every system that survives long enough becomes its own worst enemy. This 7-cluster mind map is the backbone of everything that follows. In the next chapter, we go deep into clusters 1 and 2, and I will show you the exact org structure decision that caused Italos Hasasimini platform to be rewritten from scratch 3 years after launch. Let me ask you something uncomfortable. You have a system that was clean, elegant, and fast when it launched 3 years ago. Now it takes 6 developers just to add a single feature. Nobody designed it this way. Nobody chose chaos. And yet, here you are. This is not a management problem. This is physics. Manny Lehman, in 1974, formally described what every senior engineer eventually learns the hard way. That is used must be continually adapted, and as it is adapted, its complexity increases unless work is done explicitly to reduce it. Lehman gave us 8 laws, but 3 are mission critical for your career. Law 1. Continuing change. A system must be continually adapted, or it becomes progressively less satisfactory. Law 2. Increasing complexity. As a system evolves, its complexity increases unless work is done to maintain or reduce it. Law 3. Self-regulation. The system evolution process is self-regulating, with close to normal distribution of measures of global and product attributes. Here is the insight that changed how I run projects. Complexity growth is not an accident, it is the default trajectory. Entropy always wins unless you fight it deliberately. The moment you stop paying the refactoring tax, you are borrowing complexity at compound interest. I have used Lehman's laws literally as a budget justification document, handed it to a CFO to explain why we needed a full quarter of 0-feature refactoring sprints. It worked. Because it is not opinion, it is a law. And coming up next, you will see exactly starting over from scratch to escape complexity is almost always the worst decision you can make. In 2018, a fintech client called me in after their 18-month microservices rewrite had collapsed. 40 engineers, $2 million, 18 months, and on go-live day, the new system could not process more than 300 transactions per second. The old monolith, which everyone hated, handled 3,000. What went wrong? They violated Gall's law. John Gall stated it in 1975, has never been wrong. A complex system that works variably evolved from a simple system that worked. The inverse is equally true. A complex system designed from scratch never works and cannot be made to work. You have to start with a working simple system. This is exactly why the strangler fig pattern exists. You do not kill the old system on day 1. You grow the new system around it, route one endpoint at a time, prove it works, then strangle the old one gradually. The fintech team tried to design the entire target state microservices architecture up front and build it all simultaneously. They had no working simple system at any point during 18 months of development. When I took over, we rolled back to the monolith, identified the 3 highest traffic services, extracted them one at a time using Strangler Fig, and within 5 months system was handling 6,000 transactions per second. Same engineers, same budget rate, different law applied. Here is the question that should be bothering you right now. If Gall's law is so well known, why do senior architects keep ignoring it? The answer involves something far more insidious, and it is coming in the next scene. Here is a claim that will sound wrong until you verify it yourself. Software gets slower faster than hardware gets faster. That is Wirth's law, stated by Nicholas Wirth in 1995. Meanwhile, Moore's law was telling us transistor counts double every 2 years. So we assumed performance was a free gift from Intel. It was not. Every abstraction layer you add has a cost. Every framework convenience hides memory allocation. Every microservice boundary adds network latency. Let me give you a concrete example. I personally documented. A Java financial reporting service in 2019 ran on Spring Boot 1.5 with 512 megabytes heap, processing end-of-day reports in 40 seconds. The team upgraded to Spring Boot 2.7. Same business logic, 0 new features, just a framework upgrade. Memory usage jumped to 1.6 gigabytes. Report processing time increased to 73 seconds. The infrastructure bill tripled. Why? Spring Boot 2.7 added auto-configuration classes, additional bean lifecycle management, enhanced actuator endpoints, and micrometer metrics. All turned on by default, all consuming resources for features this team never used. This connects directly to Kolmogorov complexity, the minimum description length of a program. Every abstraction that cannot be compressed away adds irreducible complexity. The practical lesson. Every major framework upgrade requires a performance baseline comparison before production deployment. But here is what makes this even more dangerous. Wirth's law and Lehman's law combine into a compounding trap, and the checklist to detect it is exactly what the next scene covers. Before we move to organization laws, I want you to use the next 90 seconds to diagnose your own codebase. These 5 warning signs are the early detection signals for complexity law violations. I have never seen a project that failed catastrophically that did not show at least 3 of these warning signs 6 months earlier. Warning 1. Your average pull request touches more than 5 unrelated files. That is layman's complexity creep in progress. Warning 2. You cannot deploy a single service without coordinating with more than 2 other teams. That is Conway's law starting to manifest as complexity. We will cover this in Section 2. Warning 3. Your sprint velocity has declined more than 30% over the last 6 months despite stable team size. Layman's continuing law is draining your throughput. Warning 4. Your last major framework or library upgrade caused unexpected regressions in unrelated modules. Wirth's law and hidden coupling are compounding. Warning 5. Nobody on your team can explain why a particular architectural decision was made more than 2 years ago. This is Chesterton's fence being violated at scale. You cannot safely change what you do not understand. If you check 3 or more of these, your codebase is actively accumulating complexity debt right now. The question is whether you will surface that to leadership before it becomes a crisis, or after. And here is exactly why that conversation is so hard to have. The organization laws coming up next are actually making your complexity problem worse on purpose. Let me tell you exactly what caused the $2 million failure from Chapter 1 at the architectural level. The company had 3 separate development teams: a platform team, a product team, and a data team. Each team had its own manager, its own roadmap, and its own deployment pipeline. The system they built had 3 layers: a platform API, a product service, and a data service. Does that structure sound familiar? It should. It is identical. And that is Conway's law in action. Melvin Conway stated it in 1967. Any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. This is not a metaphor. It is a predictable, repeatable, empirically observed phenomenon. The 3-team structure produced 3 tightly coupled services with API boundaries that mapped perfectly to manager boundaries, not to domain boundaries. Every cross-domain feature required 3 team meetings, 3 ticket systems, 3 approval chains. Now here is the power move that fixed it, the inverse Conway maneuver. Instead of designing the architecture and hoping the teams align, you design the team structure you want your architecture to reflect, and then let Conway's law work for you instead of against you. We reorganized into 2 domain teams, a customer journey team and a transaction processing team. Within 4 months, the API boundaries had organically shifted to match domain boundaries. Cross-team coordination dropped by 60%. But here is the critical insight that most articles about Conway's law miss entirely. And it is directly connected to next law that will make or break your recovery plan. So your project is late. Your manager's solution is to add 4 more engineers. This decision will make your project later. I am not being provocative. This is Brooks's law, stated by Fred Brooks in the Mythical Man Month in 1975, and it has been validated on thousands of projects in the 50 years since. The reason is pure mathematics. Communication overhead in a team grows as n times -1 divided by 2. A team of 5 has 10 communication channels. Add 3 people to bring it to 8, and you now have 28 communication channels. You nearly tripled your coordination cost to gain 60% more headcount. But it gets worse. New engineers require onboarding. During onboarding, they consume senior engineer time, the exact resource you are most short of. Brooks estimated that adding 1 person to a late project delays it by roughly the onboarding duration plus integration time. I witnessed this on a healthcare platform project in 2021. The team of 7 was 6 weeks behind schedule. Management added 5 contractors. The contractors needed 2 weeks of onboarding. During those 2 weeks, 3 senior engineers spent 50% of their time in knowledge transfer. The project delivered 11 weeks late instead of 6. The additional contractors added $40,000 of cost and -5 weeks of schedule progress. The correct intervention is almost always the opposite of adding people. Reduce scope, extend timeline, or cut non-critical features. The formula is not a theory, it is a diagnostic tool. And the question you need to ask your manager is not how many people can we add, but rather something that Parkinson observed about time itself. And it is coming next. Here is a question I ask every tech lead I mentor. Why do tasks always seem to take exactly as long as the time you allocated for them? Not less. Never less. Always exactly as much time as was available. The answer is Parkinson's law. Work expands to fill the time available for its completion. Cyril Northcote Parkinson wrote this in 1955 for The Economist as satire, and accidentally described one of the most powerful forces in software project management. If you estimate a feature at 2 weeks, it will take 2 weeks, if the core implementation could be done in 3 days. The remaining 11 days will be spent on edge cases that were never required, refactoring that was never requested, and meetings that could have been emails. This is why agile sprints exist. The fixed 2-week sprint is not about velocity measurement. It is about weaponizing Parkinson's law. By constraining time, you force prioritization. You force the team to decide what is actually necessary versus what is merely nice to have. I ran an experiment on my own team in 2020. We took a feature backlog that had been estimated at 12 weeks and challenged the team to deliver the core value in 4 weeks using time boxing. They delivered 80% of the user value in the 4 weeks. The remaining 20%, the original 12 weeks worth of scope, was never built, and not a single user complained. The practical application: never give open-ended time estimates, always time box. But here is the uncomfortable reality. Parkinson's law and Brooks's law together create a trap that most tech leads walk directly into. And the summary coming next shows you 3 specific moves to escape it starting this week. Let me close this chapter with 3 decisions you can make this week, not next quarter, not after the next planning cycle, this week. Decision 1. Map your current team structure against your system architecture diagram. Anywhere the boundaries do not match, you have a Conway's law violation, actively generating coordination cost. Pick the worst one and start the conversation about alignment. Decision 2. If you are currently on a project that is running late, count your current team size and calculate the communication channels using n times n-1 divided by 2. Then write down what scope you could cut instead of adding headcount. Bring that list to your next steering committee. Decision 3. Look at your current sprint or milestone. Find the task with the most open-ended time estimate time box it to 40% of the current estimate. Force the scope conversation now, not at the deadline. These 3 moves come directly from Conway, Brooks, and Parkinson, 3 laws that have been describing software project failure for over 50 years. The engineers who know these laws and act on them are the ones who get called architects. The ones who do not learn them the hard way, usually at the cost of someone else's $2 million. Now, we have addressed why systems grow complex and why organization amplifies that complexity. But there is a third dimension that most architects completely overlook until production burns: quality and performance laws. And what you are about to see in the next chapter will permanently change how you write acceptance criteria and define done. Let me open with a number that should make every project manager uncomfortable: 100. That is the cost multiplier Boehm's law gives us when a defect survives all the way to production. Barry Boehm documented this in Software Engineering Economics in 1981. And 4 decades later, teams are still paying the price for ignoring it. I watched it happen firsthand on a mid-tier Korean commercial bank's core banking modernization project in 2019. The deadline pressure was real. Go live was tied to a regulatory submission date. The project sponsor made a decision that felt rational in the moment. Skip user acceptance testing, move straight to production cutover, patch issues post-launch. Within 72 hours, duplicate transaction records were being written to the ledger. The defect: a 2-line mapping error in the account transfer module, something any junior QA engineer would have caught in day 1 of UAT. The fix itself took 4 hours. But the forensic audit, regulatory reporting, customer compensation, and emergency and on-call costs totaled over 800 million Korean won. The original UAT budget: 12 million won. That is your cost curve in the real world. Boehm's model shows us 4 phases: requirements, design, coding, and production. And the cost to defect roughly multiplies by a factor of 5 to 10 at each crossing. This is the shift-left principle. Move your quality gates earlier, not later. The painful irony of that banking project is that the team thought they were saving time. They were actually purchasing the most expensive bug fix of their careers. But here is what makes Boehm's law even more dangerous in modern agile environments, and we will see exactly why in the next scene. And now that we understand why bugs are expensive, the next question is, where do they come from? And the answer is not random. It never is. The Pareto principle, the 80-20 rule, applies to software defects with almost eerie precision. In practice, roughly 80% of your production bugs originate from 20% of your codebase. This was first formalized in SAR quality research by Capers-Jones and later validated repeatedly across Microsoft's internal studies in the early 2000s. But here is what most teams miss. You do not have to wait for QA to find those hotspot modules. The signal is already sitting in your version control system. I led a platform migration project for a logistics SaaS company, 12 microservices, 2 years Git history. Before we even started QA planning, I ran a simple commit frequency analysis. Sort every file by number of bug fix commits in the past 18 months. The top 20 files, out of 800, accounted for 73% of all bug fix commits. 3 of those files were in a single pricing calculation service. We assigned 2 senior engineers exclusively to that service for 6 weeks before integration testing began. Defect escape rate in that service during UAT, 0. The Pareto lens transforms QA from reactive firefighting into predictive surgery. You are not guessing where to look, you are letting the commit log tell you. The table on screen shows you exactly how to structure this analysis in your next sprint. But knowing where bugs cluster is only half the story. What happens when your team starts optimizing the wrong signal entirely? That is Goodhart's law, and it is coming next. Goodhart's law was originally formulated by British economist Charles Goodhart in 1875, and it states this: when a measure becomes a target, it ceases to be a good measure. It was designed to describe monetary policy failures, but it describes software teams with surgical accuracy. Here is the exact failure pattern I have seen repeated on at least 6 enterprise projects in my career. A VP of engineering sets a mandate. All teams must achieve 90% code coverage by end of quarter. The intent is noble: more coverage, fewer bugs, better quality. What actually happens? Developers write tests for getters, setters, constructors, and toString methods. They mock out every external dependency so nothing actually executes. They hit 91% coverage in 3 weeks. And then a critical payment processing workflow, one that requires a 6-step sequence involving 3 services, ships with 0 meaningful test assertions, covering its failure paths. I reviewed the coverage report on one fintech project and found a service with 94% line coverage that had never once tested what happened when the downstream payment gateway returned a timeout. That gap caused a 3-hour payment outage during a peak period. Coverage was the measure. Coverage became the target. Coverage stopped measuring quality. The antidote is not to abandon metrics. It is to use multiple, orthogonal metrics simultaneously so gaming one does not satisfy the system. Mutation testing scores, branch coverage on business logic paths, and defect escape rate together are much harder to game than a single line coverage number. But even if your metrics are healthy, your team might still be optimizing the wrong thing at the system level. And that is exactly where our performance laws begin. Before we move into performance laws, let us crystallize the quality cluster into 4 diagnostic questions you can bring to your very next sprint review. These are not theoretical. I use this exact checklist as a consulting tool when I am called into a project that has quality problems but cannot identify the root cause. Question 1. Are we tracking defect injection phase? If you cannot tell whether a bug originated in requirements, design, or code, you cannot apply Bohm's law to prioritize earlier detection. Question 2. Have we run a comet frequency HOTS analysis in the last 90 days? If not, you are doing QA by intuition, not data. Question 3. Can anyone on the team name a test that would fail if our most critical business rule broke? If the answer is silence, your coverage numbers are lying to you. Goodhart is in the room. Question 4. Are your quality metrics visible to business stakeholders, or only to engineers? Metrics that are hidden cannot be gamed, but they also cannot drive organizational behavior. Visibility is a prerequisite for accountability. For questions, 15 minutes, and you will know exactly which of these 3 laws your team is violating right now. Now, we switch gears entirely. Quality tells you what broke. Performance laws tell you why making it faster is harder than your architects. And the first law here will permanently change how you evaluate any scaling proposal you ever receive. Here is a scenario I have watched destroy architectural credibility in a boardroom. A system is slow, the business is frustrated, and an architect walks in and says we need to add more servers. Let us scale from 8 cores to 64 cores and the problem is solved. The business approves the budget. The hardware is provisioned. The system gets faster by a factor of roughly 2.8. Not even 4. 2.8. The architect is humiliated. The business loses trust. And the root cause is a law that has been known since 1967. Amdahl's law. Gene Amdahl derived a simple but devastating formula for parallel speedup. If a fraction p of your program can be parallelized, the maximum theoretical speedup you can ever achieve, regardless of how many pressers you add, is 1 divided the quantity 1 minus p. So if 20% of your code is inherently serial, database locking, sequential file writes, a single-threaded message broker, then your absolute ceiling on speedup is widened by 0.2, which is 5 times. You can add 1,000 cores and you will never exceed 5 times improvement. On the project I am describing, an insurance claims processing platform, the serial fraction was actually closer to 65% due to a centralized ORAC sequence generator that every parallel worker had to wait on. Amdahl's formula said the ceiling was 1 divided by 0.65, approximately 5.4x. They added x more hardware. They got 1.4 times actual improvement. The sequence generator. The fix costs 3 weeks of refactoring, not 3 months of hardware procurement. Amdahl's law is your first architectural filter. Apply it before you approve any horizontal scaling proposal. But what if the hardware itself is the constraint? That question leads us directly to Moore's law, and its very inconvenient slowdown. Moore's law is one of the most famous predictions in technology history, and one of the most dangerously misunderstood by software architects. Gordon observed in 1965 that the number of transistors on a chip roughly doubled every 2 years. For 5 decades, this observation held with remarkable fidelity, and its side effect was extraordinary. Compute faster and more energy efficient at a reliable exponential rate. Entire architectural philosophies were built on this assumption. Do not over-optimize today, the hardware will catch up. Vertical scaling is always cheaper than refactoring. Just wait 2 years and the problem solves itself. Around 2015 to 2016, the curve began to bend. Physical limits of silicon lithography, quantum tunneling effects at sub-10 nanometer scales, and thermal dissipation constraints began slowing the doubling cadence. The performance per watt improvement curve, arguably more important than raw transistor count for cloud economics, has flattened significantly. What does this mean architecturally? It means assumptions baked into legacy systems designed between 2000 and 2012. Assumptions about cheap vertical scaling, about RAM becoming irrelevant, about network bandwidth being effectively free, are now architectural debt, not engineering conservatism. I reviewed a data pipeline architecture in 2022 that was designed in 2008 with an explicit comment in the design document. This bottleneck will be resolved by hardware improvements within 3 years. That comment was 14 years old. The bottleneck was still there. Moore's law had not saved them. The lesson is precise. Software architecture must now own its own performance. Hardware is no longer a free escalator. And if you think cloud autoscaling solves this, Little's law is about to complicate your day. Little's law is the most underutilized tool in every platform architect's toolkit, and I will prove that to you with one real scenario. The law itself is elegantly simple. L equals lambda times W. L is the average number of items in a system. Think requests in flight. Lambda is the average arrival rate, requests per second. W is the average time each request spends in the system, your response time. That is it. 3 variables, 1 equation. Transformative predictive power. In 2021, I was brought in to help a South Korean fintech company prepare their payment API gateway for a promotional Black Friday event. They expected a 6x traffic surge. Their baseline: 500 requests per second, average response time of 200 milliseconds. Using Little's law, L equals 500 times 0.2, which is 100 concurrent requests in flight at steady state. Now we model the surge: 3,000 requests per second. If response time stays at 200 milliseconds, 600, it's still manageable with their thread pool configuration. But here is the insight: response time never stays constant under load. As the thread pool saturates, queuing begins and W increases. I built a simple spreadsheet model. At what point does W increase to 800 milliseconds? Lambda at 3000 means L hits 2400. Their connection pool limit was 256. Saturation, cascading timeout failure, was mathematically certain at approximately 2 times their expected surge load, not 6. We identified this 3 weeks before the event. We pre-scaled the connection pool, introduced a circuit breaker, and added queue depth monitoring with an automatic shed load threshold. The incident. Little's law did not require a load test to predict the failure. It required a spreadsheet and 20 minutes. Now let us bring all 3 performance laws together into one framework you can use in your next architecture review. Every scaling conversation in your architecture review should pass through 3 filters before a single line of infrastructure code is written. Filter 1. Amdahl's scaling. Before you approve horizontal, you must know your serial fraction. If you cannot answer that question, the scaling budget is being spent hope, not engineering. Filter 2. Moore's reality check. Identify every architectural assumption in your system that was made before 2015 and relied on hardware improvement to solve a performance problem. Those assumptions are now technical debt with compounding interest. Filter 3. Little's law saturation model. Build the L equals lambda W spreadsheet for your critical service paths. Calculate at what arrival rate your system saturates given current W values. Set your monitoring thresholds there, not at round numbers. These 3 laws together form a performance governance framework. Takes about 2 hours to apply to any system, and will prevent the category of architectural failure I described in every scene of this section. Senior engineers do not guess at performance, they model it. And now that we have covered quality laws and performance laws, you are equipped to defend your systems against the most common failure modes in the code itself. But here is what I have deliberately saved for the next chapter. The failures that are not in the code at all. Communication breakdowns, estimation disasters, and the psychological laws that govern how teams deceive themselves about project status. Those are the laws that end careers at the senior level, not bugs. Chapter 4 is where the real danger lies. In 2019, a major fintech platform collapsed its entire partner ecosystem. Not because of a security breach, not because of a server outage, but because one API response field changed its data type from string to integer. 17 partner integrations broke overnight. The on-call team spent 72 hours in incident response. And the root cause? Nobody had heard of Postal's law. John Postal, the architect of TCP/IP, stated it simply: be conservative in what you send, be liberal in what you accept. This is the robustness principle. In REST API design, this means your service should accept loosely formatted inputs, extra white space, flexible field ordering, nullable optionals. But your output must be precise, versioned, and strictly typed. The fintech team did the exact opposite. They were strict about what they accepted, meaning they broke callers frequently, and they were liberal about what they sent, meaning they changed output formats without warning. Every senior architect I've coached who truly internalized Postal's law has 0 integration outages on their record. Those who ignored it average 3 per year. But here's the twist: following Postal's law alone is not enough. Because even when your contract is explicit and strict, something invisible can still destroy your API. We'll see exactly what that is in the next scene. Here is a law that will make you rethink every API change you've ever called non-breaking. Hiram's law, formulated by Google engineer Hiram Wright, states this: with a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. Let me make this concrete. In 2021, a logistics platform decided to rename a JSON field from st to timestamp in their shipment event API. The field had never been in the official documentation. It was an internal artifact that leaked into responses. The team classified it as a non-breaking change. They were wrong. Within 48 hours, 200 downstream consumers, mobile apps, warehouse scanners, third-party analytics filed incident reports because they had all independently discovered its, written parsers for its, and shipped that code to production. The observable behavior had become de facto contract. This is Hiram's law in action. It means that the larger your user base, the more brittle every undocumented behavior becomes. As a senior engineer, your responsibility is to treat observable output as a binding contract from day one, not from the day someone complains. Now let's put Postal and Hired by side and see just how different the outcomes were when teams took them seriously. Now let's make the cost visible. I want to show you a direct comparison between 2 teams working on the same microservices migration project inside the same enterprise. Same budget, same headcount, same timeline. Team Alpha had read Postal. They documented explicit API contracts using open API specs before writing a single line of implementation. They versioned every endpoint. They ran consumer-driven contract tests in CI. Team Beta relied on implicit behavior. No versioning strategy. No contract documentation. Changes were communicated through Slack messages and tribal knowledge. When the migration hit the integration phase, the results were staggering. Team Alpha completed migration in 3 weeks. Team Beta took 24 weeks. The cost difference was 8x. Not because Team Beta's engineers were less skilled, they were equally experienced. The difference was entirely structural. Miscommunication is not a people problem. It is an architecture problem. Postal gives you the discipline to design interfaces. Hiram gives you the humility to respect all observable behaviors. Together, they prevent the most expensive category of bugs in distributed systems, the ones nobody sees coming until production explodes. But knowing the laws is only half the battle. You need an actionable checklist before you merge that next API change. Coming up immediately. Before you merge your next public API change, answer these 3 questions. Have you defined what your contract explicitly promises, not what it incidentally delivers? If your answer relies on they'll figure it out from the code, you're already in Hiram territory. Second, have you run consumer-driven contract tests against every known downstream integration? Not unit tests, contract tests. The difference is the difference between 3 weeks and 24 weeks. Third, is your change backward compatible according to Postal? Is your output strictly typed and versioned, even if your input is flexible? If you cannot answer yes to all 3, the merge is not ready. Tape this checklist to your PR template. I've seen teams add it to their definition of done and eliminate API-related incidents entirely within 2 sprints. We've now covered the full communication cluster, but here's the uncomfortable truth waiting in the next section. Your APIs can be perfectly designed, and your project will still be catastrophically late. Because estimation is broken in ways that even experienced engineers refuse to believe until they see the data. I want you to think about the last time you estimated a project correctly on the first try. Take a moment. I've asked this question to over 400 engineers in workshops across the past decade. Fewer than 8% to raise their hand. The rest smile with the specific exhaustion of someone who has been humiliated by a deadline. This is not incompetence. This is Hofstadter's law. Douglas Hofstadter, in his 1979 Pulitzer-winning book Del Escher, wrote, "It always takes longer than you expect, even when you take Hofstadter's law into account." Read that again. Even when you account for the delay, you're still wrong. This is recursive pessimism. It's not a joke. It's a mathematical property of complex system estimation. Let me show you the real cost. In 2017, Audin rescue an ERP rollout for a mid-size manufacturing company. The original estimate was 8 months. The team knew ERP projects run long, so they added a % buffer, bringing it to 10 more months. They were done in 22 months. They had applied the law and still violated it. Why? Because Hofstadter's law isn't just about adding time. It's about the fact that every new estimate you create contains the same cognitive biases as the original: anchoring, optimism bias, scope blindness. The buffer estimate is infected by the same disease as the original estimate. But before you despair, there are specific counter techniques that actually work. First, let's look at the second law that makes this even worse. Hofstadter's law explains why projects start late. The 90-90 rule explains why they never seem to finish. Tom Cargill of Bell Labs coined it. The first 90% of the code accounts for the first 90% of the development time. The remaining 10% of the code accounts for the other 90% of the development time. That adds up to 1%, which is exactly what you experience in production. Let me give you the most painful example I've ever witnessed personally. In 2020, a client's internal analytics dashboard project entered what the team confidently called the final stretch. 20% done, 2 weeks to launch. I heard those words. 6 months later, they were still in the final stretch. The reason the last 10% is so lethal is that it contains everything nobody planned for: edge case handling, error state UI, accessibility compliance, security hardening, performance profiling under real data volumes, stakeholder feedback loops, and the integration glue between subsystems. None of these appear on the original feature list. All of them block production readiness. The 90-90 rule is not about poor engineering. It is about the systematic invisibility of completion criteria. Teams measure progress by features built, not by production readiness achieved. The moment you hear a team say we're almost done, activate your 90-90 alarm. Have you defined done as deployed, monitored, and documented in production, or as code committed to a branch? The answer will tell you everything. But here's the good news. There are 2 techniques that actually defeat these laws. Let's look at them now. So if Hofstadter and the 90-90 rule make estimation structurally broken, how do the best teams actually produce reliable estimates? 2 techniques have the highest evidence base. The first is reference class forecasting, developed by Nobel laureate Daniel Kahneman and Amos Tversky. Instead of estimating from the inside, asking how long will this specific project take, you estimate from the outside. How long did the last 5 projects of this type and size actually take? You ignore your intuitions about this project. You look at historical data. In a study of IT projects I reviewed for a financial services firm, teams using reference class forecasting reduced estimation error by 40% in the first quarter of adoption. The second technique is 3-point estimation, used in PMI's PM-BOK framework. For every task, you define 3 values: optimistic, most likely, and pessimistic. The weighted average formula is O plus 4 times M plus P divided by 6. This forces engineers to articulate their worst-case scenario explicitly, which is exactly the cognitive step that optimism bias suppresses. A Scrum team I coached moved from an average estimate accuracy of 52% to within 2 sprints after adopting 3-point estimation for story sizing. The process works because it externalizes the cognitive bias instead of hiding it inside a single-point guess. 2 proven techniques: 40 to 50% improvement in accuracy, and they take less than 10 minutes per estimation session to apply. Let's close this cluster with a summary. We'll make all of this stick. Let's lock in the estimation cluster before you leave this chapter. 2 laws and 2 techniques. Hofstadter's law tells you that even your buffered estimate is wrong, because the buffer was created by the same biased mind that made the original error. The 90-90 rule tells you that the last 10% of software is where most of the real work hides, invisible in your feature list and deadly to your launch date. Counter them with reference class forecasting. Look backward at real history before you look forward at optimistic plans. And 3-point estimation. Force your team to say the pessimistic number out loud, because the number they're afraid to say is usually the true number. These are not soft skills. They are engineering disciplines, backed Nobel Prize research, and validated in real projects. Every planning session you run from now on should start with these 4 items on the whiteboard. And now we're ready for the final frontier. In the next chapter, we enter the world of change laws, the laws that govern what happens when software meets the real world and reality starts pushing back. Specifically, we'll meet layman's laws of software evolution and the architect's playbook for surviving entropy at scale. If you've ever watched a well-designed system slowly turn into a maintenance nightmare, the next chapter will explain exactly why and how to fight it. Let me tell you about a system I audited in 2019. A financial settlement platform that had been running for 14 years with zero scheduled refactoring. The team called it stable. I called it a ticking clock. Layman's laws of software evolution, particularly Law 1, continuing change, and Law 2, increasing complexity, tell us something mathematically brutal. A real-world software system must be continually adapted, or it becomes progressively less satisfactory to its users. This is not a preference. It is a law. By 2019, that settlement platform had accumulated 340,000 lines undocumented business logic. Every new regulatory requirement required touching code written by engineers who had retired. The complexity had grown not linearly, but exponentially, exactly as Layman's Law 6, continuing growth, predicts. The system didn't fail dramatically. Aged, became slower to change, more expensive to maintain, and ultimately it was placed at 40 times the original estimated cost. Layman published these laws in 1974 and updated them through 1996. 50 years later, I still walk into projects where nobody has heard of them. The question you should be asking right now is the oldest, untouched module in your current codebase, because that module is already aging, and the next scene will show you the most dangerous mistake engineers make when they finally decide to touch it. In 2021, a team I was advising inherited a microservices platform from an acquisition. During a cost optimization sprint, a sharp junior engineer found what looked like dead code, a circuit breaker wrapper around an internal payment validation service. The wrapper had 0 recent invocations in the logs. The engineer deleted it with confidence and deployed on a Friday afternoon. That following Monday was Black Friday Eve. Traffic spiked, payback posinte. The payment validation service, suddenly unprotected, receiving direct hammering from 3 upstream services simultaneously. It collapsed. The cascade took down checkout for 6 hours. Revenue loss, $2.3 million. This is Chesterton's fence, one of the most underrated principles in software architecture. G.K. Chesterton wrote in 1929, "Do not remove a fence until you understand why it was built." The circuit breaker was not dead. It was dormant. It existed precisely for the traffic conditions that had never occurred during the team's observation window. The rule I teach every tech lead is this. Before you delete any infrastructure code, ask 3 questions. 1. What failure condition does this guard against? 2. When was the last time that condition occurred? 3. Can you reproduce the condition in a lower environment before removing the guard? If you cannot answer all 3, the fence stays. Here is the deeper lesson. In legacy systems, silence is not evidence of uselessness. Silence is often evidence of a protection that is working. And that distinction will define the next principle we examine. Fred Brooks described the second system effect in The Mythical Man Month in 1975, and I have watched it destroy 2 major rewrite projects in my own career. Here is the pattern. An engineer builds their first system under tight constraints, limited time, limited resources, limited authority. They make hard trade-offs. The system ships, succeeds, and that engineer is now trusted. When the second system comes, they have authority, budget, and the accumulated frustration of every feature they had to cut from System 1. The second system becomes a monument to everything that was once impossible. I watched this unfold at a logistics company in 2017. Team A was given 18 months to rewrite a warehouse management system. They had 4 senior architects, all brilliant. Every stakeholder who had ever complained about the old system had a seat at the table. The result: a system with 14 integration layers, a custom DSL for warehouse routing rules, a machine learning module for predictive pallet placement, and a blockchain audit trail that nobody had asked for. It was 18 months late and never reached production. Team B, at a different company in the same year, rewrote a similar system in 9 months. Their rule: solve only the problems that caused actual incidents in the previous 24 months. Nothing else. That system is still running today. The second system effect is not about incompetence. It is about the seduction of finally having permission. The antidote is ruthless constraint. Write down the 3 problems the new system must solve and treat every additional feature as a threat. How does this connect to the full landscape of all 56 laws? That synthesis is exactly what the next section delivers. We have now covered all 7 clusters across this lecture series, and I want to show you something that took me years to build. A unified map of how these 56 laws interact with each other. Because here is the insight that separates a senior architect from someone who has simply read the laws. The laws do not operate in isolation. They form a dependency graph and violations cluster. Conway's law says your system architecture will mirror your team communication structure. That directly feeds Brooks' law. Adding engineers to a project makes it later. Conway has already locked the architecture to the existing team topology. Now Goodhart's law enters. When velocity becomes the metric, engineers game it. And the Pareto principle's 80-20 distribution of value gets corrupted. Your team is shipping the 80% of features that represent 20% of user value faster than ever. Meanwhile, Hofstadter's law is quietly doubling your estimates. These 4 laws are not independent risks. They are a compound failure cascade. The mind map I am showing you now is the reference I carry into every architecture review. Left branches represent complexity and structure laws. Right branches represent human and process laws. The center node is the system under design. When I see a project in trouble, I do not ask what went wrong. I ask which cluster of laws is currently being violated, and which law in that cluster is the root cause. Diagnostic discipline is what the next scene converts into a practical decision table you can use tomorrow morning. Theory without a decision framework is just trivia. So here is the practical tool I give every tech lead I mentor. A law selection table organized by project risk type. When you are facing a specific risk in an architecture review, you do not need to recall all 56 laws. You need to know which 3 or 4 are most lethal for that risk category. For team scaling risk, Conway and Brooks are your primary laws. Dunbar's number is your structural limiter. For legacy migration risk, Chesterton's fence and Lehman's continuing change are non-negotiable. For API design risk, Hiram's law and Postal's law define your contract strategy. For performance optimization risk, Amdahl's law sets your theoretical ceiling, and Pareto principle tells you where to focus first. For estimation and planning risk, Hofstadter and Parkinson are your calibration tools, full stop. I have seen architecture reviews that lasted 3 hours produce no actionable outcome because the discussion was too abstract. When I facilitate a review, I open with this table. I say, tell me the top 3 risks on this project. Let's look at which laws govern each risk, and let's check our current design decisions against those laws explicitly. That single discipline has prevented more production incidents than any amount of automated testing I have ever prescribed. The table on your screen right now is not exhaustive. It is a triage tool. And the next scene will show you what happens when are violated simultaneously on a single project, and nobody had this table. I want to end this cluster with a real project post-mortem that I was brought in to analyze in 2022. An e-commerce platform had spent 26 months building a new order management system. It launched, crashed within 72 hours, and was rolled back. The investigation revealed 4 laws had been violated simultaneously, and not one of them had been named during any architecture review. Layer 1. Conway's law. The team was organized into 8 siloed squads by business function. Predictably, the system had 8 tightly coupled services that could not be deployed independently. Layer 2, Brooks' law. At month 18, the project was running late, so the organization added 12 new engineers. Velocity dropped for 3 months. The new engineers introduced integration patterns inconsistent with the existing ones, and nobody had the authority to enforce standards. Layer 3, Goodhart's law. The engineering director had set deployment frequency as the key metric. Teams began deploying partial features flagged off, technically deploying, but delivering 0 user value. The Pareto principle's 80-20 distribution of value was completely inverted. Layer 4, every milestone had been estimated without recursive adjustment. The final 10% of integration work took 7 months. If any single architect in that room had walked in with the law selection table we just reviewed, if that our top risk is team scaling, let us run a Conway tech right now, the outcome would have been different. This is not hindsight. These laws have been documented for decades. The senior developer's job is to name the law before the failure names itself. And in our final chapter, we will talk about what it truly means to internalize this mindset, not just memorize the laws, but build the judgment to deploy them under pressure. Here is the brutal truth that separates senior developers from the rest. Knowing a law and using a law are 2 completely different skills. I have watched engineers recite Amdahl's law in interviews and then spend 3 weeks parallelizing the wrong bottleneck in production. Knowledge without a diagnostic habit is just trivia. So what does the habit like in practice? It is a 3-step mental loop you run at every critical project gate, planned up, and post-mortem. Step 1. Identify the pressure. What force is acting on this system right now? Complexity, time, team structure, or change velocity? Step 2. Map the law. Put to 56 laws predicts the failure mode of that pressure. Step 3. Prescribe the countermeasure before the symptom appears, not after the incident report. I call this law-based diagnosis, and the engineers who do it instinctively are the ones who get called into war rooms. In a 2019 fintech migration project I led, we ran this loop every sprint planning. When scope started drifting, we named it Hofstadter's Law and immediately re-anchored the deadline conversation. We did not fight the drift, we priced it. That single habit saved the delivery. But here is the question that should be making you uncomfortable right now. What happens when you apply the right law in the wrong context? The next scene will show you the 3 most dangerous misapplications I have ever seen in real projects. Let me give you the 3 law misapplications I see most frequently. And these are not junior mistakes. These are senior-level errors that have derailed real projects. First, applying Conway's law without the authority to reorganize teams. I have seen architects correctly diagnose that the system architecture mirrors a dysfunctional org chart, quote Conway's law in the architecture review, and then do absolutely nothing because they had no mandate to change reporting structures. Knowing the law and having the leverage to act on it are separate problems. Naming Conway's law without a change plan just creates frustration. Using Parkinson's law to justify crunch culture. Parkinson's observation, that work expands to fill the time available, is descriptive, not prescriptive. I have watched tech leads use it to argue for artificially short deadlines, to force productivity. The result was not focused work. It was hidden defects, burnout, and a 6-month maintenance disaster. The law explains a phenomenon. It does not endorse manufacturing pressure. Third, citing Amdahl's law before profiling. Engineers will calculate theoretical speed-up limits in a planning meeting before a single profiler has been run. Amdahl's law requires you to know the actual sequential fraction of your workload, a number you cannot guess. Context dependency is not a footnote. It is the entire operating condition of every law in this series. So before you deploy any of these 56 principles, ask one question. Do I have the data, the authority, and the organizational readiness to act on what this law is telling me? Because applying the right law at the wrong moment is still the wrong move. Coming up next, the complete reference map of all 56 laws, organized for rapid recall. Let us compress the entire series into a single scannable reference. We covered 56 laws across 7 clusters, and for anyone preparing for the 정보관리기술사 certification, I am flagging the highest frequency exam laws right now. Cluster 1, Complexity Laws. Brooks's Law, Cyclomatic Complexity, and Lehman's Laws are exam staples. Expect at 1 complexity question every sitting. Cluster 2, Estimation Laws. Hofstadter's Law and Parkinson's Law appear in project managed sections consistently. Cluster 3, Communication Laws. Conway's is the single most cited law in software architecture exam questions. Memorize both the original statement and the inverse Conway maneuver. Cluster 4, Quality Laws. Goodhart's Law and the Broken Windows Theory appear in quality management and technical debt questions. Cluster 5, Performance Laws. Amdahl's Law and Little's Law are mathematical. Expect calculation questions, not just definition recall. Cluster 6, Human Factor Laws. Fitz's Law, Miller's Law, and the Dunning-Kruger effect appear in UX and team dynamics questions. Cluster 7, Change Laws. Postel's Law, Hiram's Law, and the Chesterton's fence principle are critical for API design and system evolution questions. The pattern across 25 years exam observation is this. Examiners do not ask you to recite the law. They give you a project scenario and ask which law explains the failure. Practice scenario mapping, not definition memorization. But knowing the laws is only half the battle. The real question, do you have a system to apply them under pressure? The next scene gives you exactly that. We have covered 56 laws, 7 clusters, real project failures, and the diagnostic mindset that turns knowledge into leverage. Now I want to make sure this does not stay theoretical for you. The self-diagnosis PDF checklist linked in the description maps all 56 laws to concrete project scenarios. For each law, there is a 1-line trigger condition, a warning signal, and a prescribed action. Tape it to your monitor. Run it in your next sprint retrospective. If you have found this series valuable, subscribe and hit the bell. The next lecture series dives into architectural patterns, from monolith decomposition to event-driven systems, and I will map every major pattern to the laws from this series that justify or contradict its adoption. Each pattern will be paired with a real failure case and a decision framework you can use in your next architecture review. Before I close, I want to leave you with the one question that defines senior engineering maturity, and I want you to answer it in the comments below. Here it is. Think of the last project that went wrong on your team. Which one of these 56 laws, if you had named it out loud in Whelan, would have changed the outcome? Post the law and the project type. No company names needed. Your answer will help the next engineer watching this video recognize the same pattern before it costs them 6 months of their career. The laws have always been there. Now you can see them.